Okay, lateral shift, you understood, right? So what do you mean by lateral shift? So if you draw the incident ray, if you extend the incident ray, as well as if you see the emergent ray, incident ray and emergent ray will be parallel to each other. So incident ray seems to be shifted by a bit parallelly. So this shift is known as lateral shift or lateral displacement. In this one, the incident angle as well as the emergent angle will be equal to each other. Sorry, it will be same. I1 is incident angle, R3 is the emergent angle in our diagram. And R1, R2 are the angles within this glass slab. You can clearly see that. Fine. Is that clear? I'll just shift a bit. Just a minute. Okay. Now let's discuss about apparent depth. What do we mean by apparent depth? Yeah, virtual depth. You can say imaginary depth. Good. I can say virtual or imaginary, whatever the names you can call it, you can call it. Okay, I'm just taking a tub over here. Yeah. Assume that it is completely filled with water, like this. Okay. Here, beneath of it, at the bottom of the tank, I have just kept a coin like this. Okay. Let me change the ink. Yeah. Here I have taken a coin. But the thing is, by any chance, if you see straight through the coin or exact perpendicular, if you see, you'll always see that, okay, the coin is at the exact same height. The light rays, whenever they are passing through the interface, they'll try to come exactly like this. Here, incident angle as well as refracted angle will be same. We'll talk about that one too. By any chance, if you see through an angle, okay, from here you are looking, then what will happen, ma? The light ray wants to reach your eye like this. But what will happen? This is an interface. See, as this is an interface, the moment light ray touches the interface, what will happen? It will try to take a bend away. Ma. This is a denser medium as well as this is a rarer medium. So it will try to take a bend away. So you can clearly see that the light ray will try to take a bend like this. Okay, assume that you are a bit away. Yeah, from here you're watching that phenomena. But your eye will think that, okay, from somewhere the rays are coming. So your eye will try to retrace this one. The moment you start to retrace, you'll feel that from here the light rays are coming. Okay, so you see that than the real depth, you will see an apparent depth. You'll see an imaginary depth. You'll feel that, okay, the coin is here somewhere. It is not an exact bottom position. It is at a bit raised position. This raised position is known as apparent depth. It means that you are feeling that, okay, it is at a depth of this one only. Usually, what is a real depth? From here till here is a real depth. But you are feeling that the real depth is this one alone. Okay, you can mention here. This is apparent depth as well as this is real depth. Okay, we can always have a formula for real depth as well as apparent depth. You can make a statement out of it. Apparent depth, even if they are asking in your board exam, apparent depth, you can mention it as real depth by refractive index. Real depth divided by refractive index. Yeah. Even you can write it as ratio of real depth to the refractive index, like a statement. If it is asked for 2-mark question like that, along with the numerical. Fine. So hope that is clear. For board, you can make till there only regarding real depth as well as apparent depth without any doubt. Not only that, even they'll say that from Earth to some stars, there'll be change in position, apparent shift in the position of stars during sunrise as well as sunset. The advanced sunrise and delayed sunset, they'll say. Those are the applications of, I can say, the applications of refractive index. It's not applications, phenomena are the resultants. So advanced sunrise and delayed sunset. Why those things are happening? Okay, now assume that this is the Earth. Let me take the blue. So the sun is somewhere like this. So assume that this is 4 o'clock alone, 4 o'clock in the morning. And this is the horizon we'll see, right? So if I take an imaginary sphere like this, origin is nothing but an entry. Okay. So assume from here to here. If the sun crosses this origin, then you can say that, okay, the sun is rising. If the sun is crossing this origin, this side, you can say that the sun is setting. Usually, this will be the actual position of sun. But what is happening? The moment the sun is near to the horizon, you'll feel that always the sun rays will try to reach like this. Okay, they are coming from one medium to the other medium. The moment it comes to our medium, it will try to take a bend. It will try to take a bend like this. So whenever you try to retrace, instead of the original position, so you'll see that a bit of different position. Actually, I should retrace this one a bit more. Just clear a bit. Just a minute. Yeah. Instead of taking the exact position, the moment it reaches our atmosphere, so you'll feel a different position. You will see that, okay, the rays are coming from somewhere else. You'll see that the sun is already raised. This is known as advanced sunrise. So even though the sun is setting, the sunset is done already, but you'll feel that the rays are coming to you from a different location. You'll see that the sun is not set yet. These are due to atmospheric refraction. Atmospheric refraction, these things are happening. Okay, so how much delay will be there? Here we are saying that delayed sunset. And here we are saying that advanced sunrise. How much delay will be there? They'll ask. How much delay will be there? Or how much time gap will be there? Yes, there will be a time gap of 2 minutes. Okay, remember that quantity exactly. Okay, fine. So far the refraction and this part is done. Okay, first I should mention what is a rarer medium as well as what is a denser medium. I should have mentioned that way before, but as of now, let me go with this. Rarer medium as well as denser medium. If you want to define the rarer medium and denser medium in terms of speed of light, in rarer medium, what will happen to the speed of light? Is it more or less? Speed of light is more. Our speed of light is high, I can say. High in rarer medium. So same thing if you talk about here, speed of light is low. If you talk about refractive index for rarer medium is low, but for denser medium, the refractive index is high. Okay. So whenever light is entering from rarer medium to denser medium, they'll ask you questions like this: how the light will bend, and denser medium to rarer medium, how the light will bend, rarer to denser, how the light will bend. All these questions will be asked. Assume light is entering from rarer to denser. As well as one more, I'll take it from denser to rarer. There must be a bend, right? One medium to another medium. Just a minute. Now I can clearly say that, okay, if I construct a normal here, so whenever there is an incident ray like this, so rarer, this one is rarer, air is rarer medium, so it is entering into glass. So glass is a denser medium. The moment you are entering from rarer to medium to denser medium, the light will try to bend towards the normal. Okay, it's not an exact straight line. Yeah, but I can make it here. I can say ray will bend towards the normal. The same phenomenon I can take it with a different diagram. Same. I can say this is glass as well as this is air quantity. So I'm constructing a normal. Light has reached the glass already, you have taken. Fine. Assume that light has reached the glass already. So now, whenever it is passing from denser medium to the rarer medium, air is a rarer medium always. So then how the light will bend? Light will bend away from the normal. So you can clearly see that this much bending is there. Here I can say ray will bend away from the normal. Is it clear? So rarer medium, a rarer medium is the one where the speed of light is very high. Okay, denser medium is nothing but speed of light is low, and refractive index of a rarer medium is low. Refractive index of a denser medium is high. Fine. So whenever light is traveling from one medium to another medium, like rarer to denser or denser to rarer, the bending phenomena will take place in this manner. Rarer to denser, the light ray will try to bend towards a normal. So denser to rarer, the ray of light will try to bend away from the normal. Okay, just a minute. I'll quickly recap whatever we have done now till now. So we have started with ray optics, electromagnetic waves, ray optics, and wave optics, combinedly having 17 marks as a weightage. So ray optics is one of them. So whenever we are discussing about ray optics, my reflection part is deleted. Please go to the deleted portion. If there is any portion which is remaining, so I'll try to talk about at the end. So far we are starting with refraction. What do I mean by refraction? The phenomenon of bending of light when light is entering from one medium to another medium. So when light is going from one medium to another medium, it will try to take a bend. This phenomenon is referred to as refraction. Okay, see, air to glass, it is going. So within that, we'll try to discuss about laws of refraction. Okay, what do I mean by laws of refraction? First law and second law we are having. First law, everyone knows. The incident ray, refracted ray, normal should lie in the same plane. Now, normal is not a ray. Normal is perpendicular to the interface. What do we mean by an interface? An interface is a line, an imaginary line, which will separate two mediums or which will join two mediums. I can add a word over here. An imaginary line which joins or separates two mediums. Okay, two media, I can write it. Okay, two mediums you can make. Okay, second law of refraction is also referred to as Snell's law. What do you mean by that? The ratio of sine of angle of incidence to the sine of angle of refraction is equal to constant. This is known as Snell's law. Okay. Even we'll try to talk about Snell's law a bit later as a case 2. Then we'll try to go to refractive index. What do you mean by refractive index? The ratio of speed of light in vacuum to the speed of light in any medium is known as refractive index. And refractive index will not have any units. It is a dimensionless quantity too. Okay. And one more thing, why do we need to take the refractive index? Always I should have a measure, right? So whenever we are going from one medium to another medium, the speeds are changing. So whenever if you want to measure how the speed is changing, by what fraction, you are trying to take the refractive index. By what fraction, whether it is doubling or decreasing by 1/2, decreasing by 1/3, like that we are taking. So relative refractive index, instead of comparing with speed of light, if you are comparing the speeds in two different mediums, then you can say it as relative refractive index. There you can write it as, say, eta1, 2. Refractive index of first medium to the second medium, I can write it as eta1 by eta2. We'll try to solve some sums too a bit later case. Yeah, even you can refer this, that we have taken it as principle of reversibility. Okay, Fermat's principle is the smallest one. You won't get it in your board too. But let me tell you, light always wants to travel in the quickest path possible, not the shortest path. Somehow, only light knows the quickest path possible. So when we come to the principle of reversibility states that the moment you try to reverse the final ray path, you'll try to go in the exact same way. This is known as principle of reversibility. Okay. If the final path of a ray, after which it has suffered several reflections and diffractions, if it is reversed, then it retraces the same path exactly. That is known as principle of reversibility. Then if we come to the lateral shift, incident ray, try to extend it. The emergent ray also try to extend it. You can clearly see that emergent ray as well as incident ray are parallel to each other. Okay. So this, you can see that incident ray seems to be shifted a bit parallelly. This shift is known as lateral shift, or it is displaced by a bit. This is known as lateral displacement too. Is that clear? Okay. We'll try to talk about apparent depth. Apparent depth is nothing but a bit imaginary depth. Whenever light ray is traveling from water to air, you can see that it is taking a bend. This is denser medium. This is rarer medium. Whenever light is entering from denser medium to rarer medium, you'll try to bend away. Whenever the moment you see this, you'll try to retrace the path of the light. Your eye will say that, okay, the light coming from the coin is from here. The coin is here. From here, you are seeing it. So you'll see that a fake depth, an imaginary depth instead of the real depth. Okay. Apparent depth formula is real depth by refractive index. Please remember this one. As well as even we'll get advanced sunrise and delayed sunset. Before rising itself, you'll collect the rays. You'll see that the moment you retrace, you'll see that, okay, the sun is raised already. It is an advanced sunrise, we'll say. Even though the sun is set already, you'll see that, oh, sun is still here only. It is not set yet. We'll call it as delayed sunset. Due to the atmospheric refraction, we'll get this one, advanced sunrise and delayed sunset. So at the end, I spoke about rarer medium and denser medium. We'll just go through them.